All right, guys, this is really going to be an ancillary topic. Ancillary meaning it doesn't necessarily go with all the stuff we've been doing in this unit, but it's stuck in here for a reason because I'm going to use some of the phrases that I've used in this unit. But it's not really going to be shifting things around all that much, okay? But we will be doing a little bit of reflecting, so we'll talk about that. Guys, I got a bunch of words here, okay? And right now, these words aren't going to mean anything. It's sort of a functional notation of what I'm about to show you guys. It's going to make a lot more sense when I show you the graph and when I give you the words. So I'm going to start with that, Briggs, okay? I'm going to start with the graph, I'm going to start with the words, and then we're going to come back up and talk about what this notation means. Deal? Okay. Here's what you got to know, okay? An even function, Briggs, is going to be a function that is symmetrical to the y-axis. Symmetrical to the y-axis. What does symmetrical to the y-axis mean? If you took geometry last year, you should have a pretty good understanding of what that phrase means. Symmetrical to the y-axis. Yeah, I mean, I actually like what you did better with your hand. Do it again. Yeah, give me another word that might correspond to something we're doing in this unit. Isn't symmetrical to the y-axis means you could see it as a reflection in the y-axis, right? Okay, so it looks like a reflection in the y-axis. Okay, that's the first thing. Okay. If I have one other thing. It usually involves x to an even. Now, guys, when I say usually, understand that it means just that. It's usually going to involve x to an even. In a minute, we're going to see something that doesn't involve x to an even, that is an even function. Okay? An odd function, okay, is going to be something that is symmetrical too. Now, immediately, everybody's going to think I'm going to say what? X-axis. But what's wrong with that? This is actually this is actually a question from your homework, or it will be a question on your homework. What's wrong with that? Why can't I have symmetry to the x-axis?
Because it's crossing.
Say it again. It wouldn't be a function, right? So if I gave you guys this, oh, okay, well then. If I gave you guys this, does that have symmetry to the x-axis? Yeah, right? But it's not a what? It's not a function, right? And that's what is wrong with the fact that I called it an odd function, right? So that can't happen, okay? So instead, what it's going to have is it's going to have symmetry to the origin. Now, when I say symmetry to the origin, again, our geometry students, remember that from last year, symmetry to the origin, point symmetry. I'm going to give you a better way to think about it, Jaden. Ready? Symmetry to the origin looks the same right side up as it does upside down. Looks the same as it does upside down and right side up. In other words, if I gave you the letter S, right? If I gave you the letter S, what's cool about the letter S? Well, if I take my paper and I spin it, looks the same, doesn't it? Right? Looks the same. So a graph that is symmetric to the origin shares that property. It's going to look the same upside down as it does right side up. Is that cool? Okay. usually involves x to an odd. Again, usually. Doesn't have to, usually does. Hence the phrase even and odd function, right? Hence the phrase even and odd function. So here's what I want to do, okay? I give you two graphs that are the beginning of a sketch. What I want to do is complete the sketch. And I want to complete the sketch of an even and an odd. So here is a picture, right? I want to make this an even function. If it's even, we said that it's going to have what? It's going to have symmetry to the y-axis. In other words, Jelani said it. It's going to look the same on this side as it does on that side. So I'm going to take what I have right now and do what? Reflect it in the y-axis, aren't I? Okay, so this point right here, do I actually have to move that at all? Why not? Because it's on the x-axis, right? Or on the y-axis, I should say. It's sitting on the y-axis, so it's not going to move. How about this point? How far away is that from the y-axis? 3. So I'm going to move it over here 3 units away. This point right here is 7 units away from the y-axis. So I'm going to put it 7 units away on the other side. Play connect the dots. And you get this. Looks like an M, right? Looks like an M. Would you guys agree that that definitely looks like symmetry to the y-axis? Okay. Now what I want to do is write down these points that I just created, okay? 0, 0. Did 0, 0 change? No. All right, so let's leave it. 0, 0 stayed as 0, 0. What did 3, 5 become? Negative 3, 5. Very good. And how about 7, negative 2? What did that become? Negative 7, negative 2. Sadie, really quickly, let's do a little bit of analysis of what we just did. Look at these points. Does anybody see something about these points? Well, these points. What do we notice about these points? Give me some things that are different, some things that are the same. Only the x's changed. What happened to the x's? They became negatives, right? What about the y's? The y's stayed the same, right? So in this picture, guys, what happened? I had a value and I got a value of a meaning some general point, okay? But then what happened? Then I negated the input and I still got the same result as an output, didn't I? In other words, I plug in 0, I get 0. I plug in 0, I get 0. The outputs didn't change. I plug in 3, I get 5. I plug in the opposite of 3 and I still get 5. I plug in 7 and I get negative 2. I plug in the opposite of 7 and I still get negative 2. Okay, that's going to be important in a minute. All right, let's go over here. This one's a little bit more difficult to do. I got to create a function, right, where it looks the same upside down as it does right side up. And I said that it's a reflection through the origin. Origin. What does a reflection through the origin look like? Well, if there's a point here and I reflected it through the origin, raise your hand if you didn't take geometry last year? Perfect. That's perfect. Caesar, come up here for a minute. Point to that. See where my cursor is? Go on up there. Just put your finger on that point where my cursor is for a minute. Sweet. Okay. And point with the other finger where the origin is. Okay, cool. So if you were going to reflect that point through the origin, generally speaking, where would it go? I don't see where your hand is. I gotta move. Hang on. Okay, so Caesar wants to go from here to here. You guys raise your hand if you agree with him, if you think that that's good. Nobody agrees with you? John agrees with you. How come nobody agrees with him? Why not? Go ahead. Where do you think you go? Yeah, go up there. Show me where do you think you would put the point? Stay right there, Caesar. Maybe you guys can duke it out or something. Maybe we can actually get like a fight. So you think it's going to go down in that bottom right or that bottom left-hand corner? Who agrees with her? Yeah, I think so, right? Like the way that I would picture it is what? If I want to reflect this point through here, it's going to what? It's going to what? Go right through there to the opposite side, the same distance away, right? So if this distance right here was like 6 feet, then that distance right there would have to be 6 feet, wouldn't that? So wouldn't that serve as like a midpoint per se of a line segment that connects this point and this point? Does that seem reasonable? Caesar, don't go anywhere because we got to make sure that you got it. So point to that other point that we didn't move, the one that's 7, -2. So based on the conversation, where do you think that point might move if we were to reflect through the origin? Yeah, over there somewhere. Absolutely, right? So can we visualize that? Can we see where it's going to go? Good, guys. Thank you. So the rule for this, guys, the rule for a reflection through the origin is actually really simple. Here's how it works. If I asked you guys to go from here to the origin, give me directions. How would I get from here to here? I would go, right? Give me, so first of all, Hazi, I want to go from here to the origin. You told me to go, yeah. I want to go from here to the origin. You said to go right. Try again. Go left. How many left? 3, and go down 5. So do you guys agree that if I were to just repeat that, I would wind up where I want to be, wouldn't I? Okay, so if I were to go left 3 and down 5, it's going to bring me, oh, I turned my radio on somehow. It's going to go there, isn't it? What is that point, guys? That's the point, -3, -5. Okay, good. And Caesar said, we're going to take this point and we're going to go over here somewhere. So how do I get from here to the origin? I go up 2 and to the left 7. So if I repeat that, up 2 and to the left 7, I'm going to wind up over here at the point -7, +2. Guys, what about 0, 0? Does that point shift, move, or change? No, right? A point that's on the origin, reflected through the origin, will stay at the origin. Connect the dots, and it looks like this. And fortunately, I'm waiting for some people to do something here. Is this odd? Is this odd? I'm waiting for some people to do something on their desk. Thanks, Marks. Yeah, she's flipping her paper upside down, right? Because what did I say? A function is odd if it looks the same upside down as it does right side up. And so if you turn your paper upside down, does it look exactly the same? It sure does, doesn't it? It sure does, okay? Guys, one more thing. In order for a function to be odd, what point does it have to go through? It's got to go through the origin, doesn't it? If it doesn't go through the origin, not going to look the same upside down as it does right side up, will it? Okay? Look at these points. Does anybody see a pattern? Both signs changed. 3, 5 went to -3, -5. 7, -2 went to -7, +2. And so the rule for this is if I have f of x equaling a, then when I change x to be the opposite, the output also changed to be the opposite. So are you saying with this piece right here?
Yeah.
Yeah, so here I changed this, and what happened here? I have an A and a negative A. Here, I changed the input, and I wound up with the outputs being the same. So here the outputs did not change. Here, the outputs were also changed. See the difference? A versus negative A. Yes. So in other words, okay, so let me give it to you this way. Here, if I plugged in 1, maybe I get 5. Here, I would plug in -1 and get -5. Over here, if I plugged in 1 and got 5, then if I plugged in -1, I would still get 5. See the difference? So here, the outputs are the same. Over here, one was different. Cool? All right. All right, so here I give you guys this function, right? Now, notice something. Did I give you a picture? No, I didn't. Okay, so watch what we're going to do. We're going to figure out if this is even, odd, or maybe neither. Maybe neither. Maybe it can't. Maybe it's neither one of them, right? Let's figure it out. It could be normal. Yeah, exactly. It could be neither one of these. These are like special cases, right? These are like some really special graphs, okay? Guys, so if I plug in 6, what's the absolute value of 6? 6. 6 minus 4? 2. All right. Well, now if I take -6 and plug it in, what's the absolute value of -6? 6 minus 4? 2. So what do you notice, guys? And this is what Trinity was saying. I plugged in 6. I plugged in the opposite of 6, and I got the same result. So far, this is looking like it's probably going to be what? Even. Even means same result. Okay? If I plug in 2, absolute value of 2 minus 4 is -2. Again, -2. If I plug in 5, absolute value of 5 minus 4 is 1. The absolute value of -5 is 5 minus 4 is 1. So, come on, Cal. Help me out here. Okay, so the outputs remain consistent. 2 and 2, -2 and -2, 1 and 1. And again, I'm looking at inputting the opposite thing, right? So based on this, this appears to be even. Right? It appears to be even. Now, watch this. You guys are smart now, so watch how this from previous lessons is going to play in. This is an absolute value graph, right? I want you to think about our previous lessons in this unit. What am I going to do to this absolute value graph? Am I going to reflect it, stretch it, shrink it, shift it? Am I going to reflect it, stretch it, shrink it, shift it? Well, it's the absolute value of x minus 4. Where's the -4? In or out? Out. Does that affect x's or y's? Y's. Is this going to shift it up or down? Down, yeah. So this is going to be an absolute value graph that's been shifted down 4 units. Well, what does an absolute value graph look like without shifting it? Well, it looks like this. So there's an absolute value graph. I did not shift that one. That's just the normal one, right? So that would be this. And now all I'm going to do is take this graph and shift it down 4 units, right? And what do you notice about that blue graph? It's a reflection in the y-axis, right? Do you guys see the symmetry that holds this direction, right? So this definitely is even, and we saw it up here with the points. Does it have the correct look? It sure does. It is reflected in the y-axis, confirming that it is even. Cool? All right, last bit. In your calculators, I want you guys to put that guy in right there, and let's fill out this table. So give me a table of values for that. What did we get when we plugged in -3? -15. And then we got 0, and then we got 3, and then we got, and 15, right? Now, what do you notice, guys? Again, I'm deciding, Sean, if this is even or odd, or maybe it's none of the above. Maybe it's just a normal graph, right? Let's look at the corresponding points, right? Let's look at, let's compare the opposite inputs. So compare this one and this one. So what did I do here, guys? In the first line, I plugged in -3 and got -15, right? Then in that last line, I plugged in 3 and got +15. So did the output remain the same? No, the output also changed to the opposite sign, didn't it? That's exactly what an odd function is, isn't it? Okay, let's make sure this works here. You plugged in -2 and got 0. You plugged in +2 and got 0. Now I can't negate 0, so that makes sense, doesn't it? Okay. And then I plugged in -1 and got 3. I plugged in +1 and got -3. So based on that, what does it appear to be? It appears to be an odd function. Okay. Now, I did not ask you guys to put this on your chart, right? But if we plugged in 4, we would have gotten 48. If we plugged in 4, we would have gotten, no, we wouldn't have, I lied. Yeah, we would have. If we plugged in 4, we would have gotten 48, okay? So, knowing this piece of information, without looking at your calculator, knowing that this is odd, you should be able to give me another point. -4, -48. Because it's an odd function. Because it's an odd function, right? Which means both signs had to what? Had to change. Sketch a graph. And let's make sure that it represents what we thought it would, right? So if we sketch a graph of this, let's see if it looks like an odd function. In other words, the right way, upside down and up and right side up. It'll look something like that, right? And anytime you're not sure, oh, Mr. Picard, I can't tell. Is it even? Is it odd? I'm not sure. Take your paper and flip it. And if it looks the same, you should be in good shape. Okay, so this lends itself to our final question of the day. Is a simple exponential function odd, even, or neither? So if I asked you guys to graph this. Now you guys who took algebra last year have the advantage now because you did some graphs of these. Exponential functions either are classified as growth or decay, meaning they either get bigger or smaller over time. And so an exponential function like this, and of course you could use a calculator, would look something like this. So that's a graph of that function. Now, first of all, is it going to look the same upside down as it does right now? No, definitely not. Is it reflected in the y-axis? No, if it was, then this going up would also have something over here going up, right? So that doesn't look any good. But Trinity, what if I wasn't sure? What if I wasn't sure? I can't really tell. Is it odd, even, neither? Can I plug a value in and figure out what happens? All right, let's do that. Let's see what happens when we plug in 1. What is 2 to the first power? Positive 2. So that means that I have a point 1, 2. Guys, if I want to figure out now if this is even, odd, or neither, what do I need to compare this to? Well, I plugged in 1, now I need to plug in -1 and see what we get. 2 to the -1 power. Now this isn't quite as easy to do. Type it in your calculator, Sean, go ahead. 2 to the -1st power. One half. So in other words, the point -1, 1/2 lies on this. So let's go through our scenarios. I plugged in 1 and -1. I got 2 and I got 1/2. It's neither, right? If it was even, I would have gotten the same result. If it was odd, I would have gotten -2. And so this is neither even nor odd. Neither even nor odd. Okay,